Hello, my name is Scott Adamson and welcome to my virtual session. As you can see on this screen, I hope you are in the right session. It's going to be a great time. It's funny to do this in a virtual setting, especially talking about active learning, and I'm talking to my camera. So I hope that you will find this virtual presentation, in spite of it being virtual, to be active. I'm going to ask you a few times during the session to stop and think. I hope you will. Let's get going. So here's a quick description of what this session is about. I'll just stay silent for about 20 seconds while you read. And yes, it's true. I will be talking about classroom tested strategies that you can take into a live face-to-face classroom and also a virtual classroom situation you'll see as we go through this session. Here's a little bit about me. I've been teaching at Chandler Gilbert Community College in Chandler, Arizona. It's in the Phoenix area. I've been teaching there for about 23, 24 years now. I've been a high school teacher also, and now a college teacher for this overall over 33 years of teaching. And there's a little bit about me and my family, just so you know who's talking to you today. I do have 4 kids and a foster son that we've had now for about 1.5 years. So enough about me. Let's get busy. Let's talk about rigor. First of all, when you think about the word rigor, if somebody said to you, is your program, is your curriculum, is your lesson, is your mathematics department, whatever you're thinking about, rigorous? I would guess that in the thought bubbles of people, just a bazillion different thoughts would come into mind. And so to kind of bring us together, let's look at a Google definition of rigor. Rigor is a sudden feeling of cold with shivering, accompanied by a rise in temperature, often with copious sweating. Is your math program, curriculum, lesson, exam, assessment rigorous in that sense? Of course, that's just kind of a joke here, the medicine definition. There are other definitions of rigor that you can find on Google. The quality of being extremely thorough, exhaustive, or accurate, severity or strictness, demanding, difficult, or extreme conditions. Is your math program, curriculum, lesson, assessments rigorous? In what sense? And then just for fun, because Google allows us to see it, the use of rigor over time is interesting to me, especially as you look out here in the last few years. There seems to be an uptick in the use of rigor. I like to joke, it's probably because we're talking about it a lot in mathematics education, and what does it mean to be rigorous? And that's a good thing. So think about what it means for you. Sometimes the idea of rigor would be something like this. I just grabbed a page from a textbook, in this case with integration, and under the context of this demanding, difficult, or extreme conditions, maybe we assign this for homework. And then we could think about, how could we make this assignment even more rigorous? How about that? Does that make it more rigorous? Or how about that? Does that even make it more rigorous? 172 integrals to solve. What do we mean when we say rigor? A lot? Demanding? Tedious? What do we mean? So in this moment, early in this presentation, maybe you could just take a moment and think about, what are you thinking right now when it comes to rigor? What is in your thought bubble? If you were asked about a rigorous assessment, a rigorous curriculum, a rigorous lesson, whatever, what are you thinking? Well, the reality is that there are different views of rigor. The Dana Center at the University of Texas at Austin, in their work with alternate pathways, has encountered several different views of rigor. Let me just share this slide with you. Among the things we have learned, one concern stands out, that changing mathematics curricula away from an emphasis on algebra may lead to less rigorous courses. Keep in mind, this is in their work with alternate pathways. The pathway that traditionally is algebra, geometry, algebra, pre-calc, calculus, something like that. And there's been some work by others, but the Dana Center for sure, about pathways that would lead to a quantitative data, big data, statistics, quantitative reasoning type pathway. And in that work, here's what they are saying, that this shift away from the traditional emphasis on algebra may lead to less rigorous courses. Well, at first, the remedy to this concern seems obvious: to ensure that the elements of rigor are incorporated into all courses. Okay, so if we're going to have these alternate pathways, wonderful, just make them all rigorous. But as we explored this situation, the Dana Center, we realized there was no consensus on a definition of rigor to apply in addressing the effectiveness of math education. What do we mean by rigor? Like my thought bubble idea, there's a bazillion different thought bubbles on what we mean by rigor. There's no consensus on what we mean. And in the Dana Center's work, they've encountered 4 views. I'm not saying that these are the correct views. These are just the views, 4 of them, big overarching views that they have encountered in their work with the idea of rigor. View number 1, the use of logical deductions from stated hypotheses to prove theorems. A curriculum, a lesson, a program that is rigorous would have this. And just as an image, as a visual, I have here a derivation of the quadratic formula. Does that make the course rigorous, that a teacher showed the derivation of the quadratic formula? And if any of you have ever done that, you likely know that at the end of this, the students probably heard something like blah, 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 and then here's the formula, let me show you how to plug numbers into it and get the right answer. Does that make the program rigorous, just that we did this logical deduction from stated hypothesis? Or another view of rigor, number 2, adhering to traditionally prescribed content. Math departments often determine course content by committee, and to be inclusive of all of its members, agree to a long list of topics and concepts that may actually undermine flexible adaptation to student needs. And again, just as a visual here, you see some typical algebra table of contents with this list of things that we're supposed to teach. And in my world, that certainly is true, that as we work on course competencies and you get math faculty from different walks of different experiences into the room, we end up with this laundry list of topics that people think need to be in the course. Is that what makes the course rigorous? That we've got all of those things. The more things you have listed, the more rigorous the course. Or how about view number 3? Rigor is synonymous with increased difficulty and more challenging content. Rigor is associated with advanced courses, comprehensive presentation and lectures on all possible topics and techniques, high stakes tests, low pass rates, low grades. A course that's really rigorous is one that has low pass rates and low grades and has some summative high stakes assessment at the end of it. And just as a visual here, I looked at a textbook that had a homework exercise section, and they had these different pieces. And the last piece was explorations and challenges. Does that make it rigorous? Or up here in the corner, there's textbooks that are advanced, or in the higher education level, advanced calculus. Or what about math for gifted students? What makes any of this rigorous? And then view number 4, and we'll end here, rigor and college algebra may be used interchangeably. In this pathway discussion, it's often the case that the pathway leading to calculus is the rigorous pathway, and the pathway leading to non-calculus is not rigorous. And so college algebra gets in the middle of that as the rigorous pathway. In this view, college algebra stands as a proxy for rigor, in part because skills developed in the course may open many other mathematical options for students, and because mastery of algebraic skills signifies readiness to proceed with a student's mathematics education. And this graphic is just pulled from Google Images, where we have this quantitative reasoning. So is this these options might be considered, well, for the less rigorous options, here you are. And then over here on the calculus pathways, for the more rigorous options, here you go, like engineering. So, does that define rigor? No. So what would we use as a definition of rigor? And back to this college algebra issue, using college algebra as a proxy for rigor unnecessarily limits the conversation about rigor to only one area, mathematics. When college algebra is used as a proxy for rigor, mathematical modeling, geometric and numeric methods, statistics, and quantitative reasoning are often labeled as not rigorous. Yet we know that all of those things, quantitative reasoning, algebra, statistics, can all be rigorous. The ability to perform algebraic manipulations, a primary objective of college algebra, in and of itself does not provide clear information about what rigor is. Consequently, understanding college algebra is not the equivalent of rigor in all mathematical fields. So what is rigor? And I'm going to again draw on some work from the Dana Center where we have this strand of ropes together, and all together we have rigor as procedural fluency and skills, which is kind of the traditional thing of just practicing, procedural fluency and skills. But what about conceptual understanding? What about persistence? What about application, problem solving? And in the Dana Center's work, they have this, I think, wonderful statement. Students' use of mathematical language to communicate effectively and to describe their work with clarity and precision. Students demonstrate that what they have done works, when it works, and why the procedure they selected is appropriate. Let's pause there for a minute. A rigorous approach would be one where students demonstrate that what they have done works, they demonstrate when it works, and why the procedure they selected is appropriate. And students can answer the question, how do we know? And another resource here from Nade and A. Maddock, and the National Math Summit back in 2018, they came up with this definition of rigor: attention to precision, structure, patterns, inference, interpretation, reasoning, mathematical habits of the mind, and ways of thinking, and helping students to develop their mathematics identity. And this little segment here I really like. In a rigorous course, students are asked to struggle with real, non-routine problems in context, identify strategies to solve problems, communicate about mathematical ideas with clarity and precision, and justify solutions. Now, when I asked you a while back to think about your ideas of rigor, I'm going to guess, because I've done this before, that some of these ideas were resonating in your head. Application and explanation and communication and problem solving and reasoning and thinking. So as we move forward here today, I'm going to come back to this definition of rigor, hopefully repeatedly, and pull out from the experiences that we're going to have through this session how a rigorous mathematics experience can be had by our students. But first, I'm going to start with a non-example, and I'm going to show you a situation here. This is from the Tokyo Olympics in the summer of 2021, where the Italian sprinter Jacobs won the gold medal by running the 100 meters in 9.79 seconds. And I like to do this with my classes to ask this question: how fast did he run? And I intentionally leave it open-ended like that. Just, hey, how fast did he run? Now, we could answer the question by saying he ran 100 meters in 9.79 seconds. But that would be the conventional way to express the speed of the runner. And so a student might do something like this. And I'm going to kind of pretend like I'm the student. So the student gets this problem and they say, well, let's see, he ran 100 meters in 9.79 seconds. And let's see, I remember the formula my teacher told me. It's dirt. Dirt, D equals RT, dirt. And if we have D equals RT, then we can divide both sides by T, and rate is distance over time. Distance over time. And we know the distance is 100 meters. We know the time is 9.79 seconds. So 100 over 9.79 is 10.21 meters per second. But maybe the student being left open-ended might think, that's kind of, I don't know about meters per second. I'm going to change it to miles per hour. And so the student continues, 10.21 meters in 1 second. And so I set up this analysis and I try to get the units to be top to bottom so I can cross off the units. And after all of that arithmetic, we get to 22.8 miles per hour. Jacobs ran 100 meters in 9.79 seconds, which is on average 22.8 miles per hour. Now, many teachers might look at this work and hearing what the student said and would think, wow, that's a rigorous example of student work. And I wonder if it really is. Is it really a rigorous example of student work based on our definition of rigor? Or is it just a student remembering what to do and mimicking some things that they've been taught to do in the past? So for example, if this was my student, I would ask some questions like, how does dirt make sense? They remember the dirt formula and they might ask, how does that make sense? Can you explain it to me? And when you said 100 over 9.79, what does over mean? You see, over doesn't have a mathematical meaning. It's just visually what you see. This number is over this number. But what do you mean when you say over mathematically? And when you do that division, it says 100 meters divided by 9.79 seconds. And if we think about what division means, we might challenge the student to think about, how does it make sense that 9.79 seconds goes into 100 meters? How do seconds go into meters? And when we get down to that unit analysis thing, the dimensional analysis, we cross out units. What does it mean to cross out units? How come we can just cross them off? Now, when we start asking these questions, we might get at some elements of rigor. And so here's a classroom activity that I would like to do. And I'm sure many of you are familiar with the 3-act task framework. And I really like that 3-act task framework. And so it might manifest something like this. Act 1. Act 1 is the hook to draw you into a situation, to solve a problem. And in this case, here's the hook via video.
Well, they got a lot of people who will stay around in a blowout game just to hope that he comes into the ball game. Flame-throwing Aroldis Chapman comes in, 7th game for Aroldis. He sat out the last few games. Oh, toothpicks for sale.
Up there.
Did not swing and miss, I don't believe, while he was up there at all. That would be a new record.
What would be a new record?
Hardest pitch ever thrown. He set the mark last year just over. That one on the guns.
Check it out.
Got him.
Got him at.
Is it different with this guy when they come back? What's it like up there? What's he throw? Is it a little different because it throws so darn hard?
Well, I think they'll come back and say gas.
1-2-3, 9th inning for Aroldis Chapman.
So hopefully you're bought into the situation, and what I like to do then is ask students, just what do you notice? What do you wonder? Another pretty common framework these days, just to get students thinking. This is that idea of a low floor, high ceiling. At this stage, all the students in the class, no matter where they're at, have had a common experience of watching a baseball pitcher throw the ball apparently really fast. And so what do you notice, what do you wonder? And it might be really obvious, but the speeds were blurred out up on the scoreboard, and I cut the audio when the announcer said how fast, and so it's probably going to become pretty obvious that the question is, or the notice and the wonder would be, I noticed that you blanked out the speed, I noticed that the audio went blank, and I wonder how fast was he throwing the ball if it was such a big deal. So then we move on to Act 2, and this is where we would find out the answer to that question. How fast was one of those pitches? And so I would want the students to request information. They would ask me, well, in order to answer that question, we're going to need this or we're going to need that. What do you need to answer the question? And I will reveal the things that I choose to reveal. In Act 2, you decide what information you want to give students. And so let's say in this case, we share some information with them. Notice the distance from the pitcher's mound to the home plate is 60 feet 6 inches. And let's assume that that pitch, one of those pitches that I'm choosing, was reached home plate in 0.389 seconds. And as we work on this problem, you might think about what assumptions are you making when you solve the problem of how fast did this pitch go? 60 feet 6 inches, 60 feet 6 inches in 0.389 seconds. Now, I think it would be great for you to just think about how you would solve that problem right now and work on a solution that maybe you would anticipate a student would respond in a rigorous setting. And let me set the framework here too, or set the stage for what audience I'm thinking about here. This is an audience of students at a level where they're just learning about ideas of rate, speed. They're learning for the first time about proportional relationships. And so in that world, we're developing the ways of thinking that would be productive for these students. So at this stage, what would a rigorous result, a rigorous response look like? So if you could pause and work on this on your own first, and then we can come back and talk about it. So as you work on the problem, consider the different aspects of rigor. Remember, what we are defining to be rigor is demonstrate that what the student has done works, when it works, and why it works. Answer the question, how do you know? How do you know you should divide? How do you know that this is how it works? Identify strategies. What ways of thinking are you going to use in this case? And the student communicates these ideas with clarity and precision. And they're able to justify their solutions, not because the justification is more than just, I followed the formula, I plugged everything in, I got the answer. The justification is flowing from a way of thinking that gets at the mathematical ideas in a profound way. So what might that look like? Well, in Act 3, we can see that. So suppose a student was thinking about the distance and the time as two quantities, and they represented those quantities as lengths. So they're thinking the baseball traveled about 60 feet 6 inches. I say about because there could be some conversation about when he actually releases the ball. Is it exactly 60 feet 6 inches? This might be one of the assumptions, is we're going to say the ball traveled the full 60 feet 6 inches, and it traveled it in a time of 0.389 seconds. So imagine that quantity as a length as well. So we could just stop there. How fast did the ball travel? 60 feet 6 inches in 0.389 seconds. But that's not very conventional, is it? That's not how we typically report speed, is a per 0.389 seconds. We usually report a speed as a per 1 unit of time. I mean, can you imagine? What if I told you that I got pulled over as I was driving to school one morning, and the police officer came to the window and said, "Sir, do you know how fast you were driving?" And I would say, "Yes, I was traveling 45 miles per half an hour." Which might be true, but 45 miles per half an hour would not be the conventional way of reporting a speed. We would say something per 1 hour, 90 miles per 1 hour. So likewise here, the first thing a student might be thinking is, how can I scale the time of 0.389 seconds to be 1 full second? So how would I do that? Well, how many 0.389 seconds are needed to make 1 second? And then this is where our previous understanding, our prerequisite skills of what division means would come in. In order to answer the question of how many 0.389 seconds are needed to make 1 second, I have to think division. That's a division question. There'd be about 2.57 copies of 0.389 to make 1 full second. And then second, they might think about, well then proportionally, if I scaled the time by a factor of 2.57, I should likewise scale the distance, because we're making this assumption that the ball is going to travel 60 feet 6 inches for every 0.389 seconds. And as I scale it up to 1 full second, that is proportionally going to work out the same. That is, every 0.389 seconds is going to have 60 feet 6 inches. So proportionally scale both. So 60 feet 6 inches needs to be scaled by a factor of 2.57 as well. Can you imagine one copy of 60 feet 6 inches, another, and then 57 hundredths of a copy? And all of that turns out to be 155.485 feet. So we've now scaled both quantities by a factor of 2.57 to get 155.485 feet per second. And now I may not request it, but my guess is that in this Act 1, Act 2 scenario, somebody in the room, and you'll see later what this might look like in my classroom, but somebody in the room might think feet per second is kind of awkward. I don't really know. 155 feet per second, is that a lot or a little? I don't know. So they might want to convert it to miles per hour. 155 feet per 1 second. Well, I need to scale up 1 second to 1 hour, and I'm kind of shortcutting this for the sake of this presentation, but there's 3,600 seconds in an hour. So if I scale the time by a factor of 3,600, I'd have to scale the distance by a factor of 3,600. But then that's kind of weird. Can you imagine? What is that? 559,746 feet per hour. So let's convert the feet to miles. How many 5280s? Something they may have to know, or Google, or ask Siri. How many feet in a mile? 5,280 feet in a mile. How many 5280s? How many 1 miles are in there? And now they're thinking, they're just wondering about this and trying to figure it out. How many feet, how many miles, how many 5,280 feet are in this 559,000 feet? Well, that's a division question. So I divide and I find out it's about 106. So 60 feet 6 inches in 0.389 seconds, all the scaling and proportionality happening here, 106 miles per hour. Now, can you imagine? I'm going idealistic here. It's a presentation at NCTM. I'm giving you the ideal view. This is what we're working towards, is students have developed ways of thinking that they can articulate how we can go from here to here. Now, after we've developed this, we can now condense this and get to nice formulas about, if you look back at this work, you really ended up just dividing and dirt, and all that stuff can still come up, but it's going to flow out of the thinking and really the development of the mathematics, not just start with this dirt formula. So imagine a student has this, and then Act 3 would be to check your work. Now, how do they check the work? Hey, teacher, am I right? No, we check the work by watching the video.
Well, the guy, a lot of people will stay around in a blowout game just to hope that he comes into the ball game. Flame-throwing Aroldis Chapman comes in, 7th game for Aroldis. He sat out the last few games.
All right, now look. 103.
Correa did not swing and miss, I don't believe, while he was up there at all. Having a 106.
106.
Record for the hardest pitch ever thrown. He set the mark last year just over 105. That one on the gun said 106. Got him at a mere 102.
A mere 102.
This guy, when they come back, what's it like up there? What's he throw? Is it a little different because it's roasted on hard?
Well, I think they'll come back and say gas.
So there you are. We can check our work against the video and see. So I hope this presents a visual and an experience of what I'm thinking about when I think about rigor in student work. Rigor in student work is not remembering what formula or what process to use. Rigor in student work is students really grappling with the ideas and having a foundation. Don't get me wrong, there's still a foundation of scaling, proportionality, division, what do all these things mean, but then they can work through a solution, and it would be fine at that stage of development than to move to the more efficient distance equals rate times timing, etc. But we should be able to unpack the distance equals rate times time and explain why and how all of that works, like maybe as you saw in my example. Let's look at another example at an Algebra 1, Algebra 2 level with a video called Mater the Greater. So Act 1, we're going to draw their attention and their interest and their motivation in by showing a video.
What happened?
I love it. What happened? It's like they made this for a math class. This is from a Pixar short. This is Mater the Greater. And a Pixar short, it's like a couple minute, 3-minute little video that I saw with my foster son. And I right away thought, oh my goodness, this has to be a math lesson because it's a perfect 3-act task. Well, what happened? And now we can engage in some mathematics. So first, what do you notice? What do you wonder? And notice I like to frame it like this. What mathematical noticing, wondering comes to mind? Because sometimes students will start with some non-mathematical noticing and wondering, which is fine. But I want to also promote the mathematical noticing and wondering. So they might notice that and wonder, did he make it across the canyon? Did Lightning McQueen survive? And so we start working on that. Hey, by the way, this one, and in the handout for this session, you'll see the link to this. But there's a Desmos activity version of this that I've created, so you could use this in a online virtual space. You could do this in the classroom. This might help guide the whole process. And it's been under development here, so it might not look quite like this anymore because I've been tweaking it as time goes on. But that is available as well. So students are noticing and they're wondering and they're thinking, and then we get to Act 2. And Act 2 is this idea of giving them some information. So I've got this for you if you would like to share this kind of stuff. Students might say, well, how far is it across from the where he left the ramp to the landing ramp? And so I did some work there. All right, here's how it goes. A sedan, I just Googled it. A sedan in real life is 184 inches in length. And on this little blip, I printed out this screenshot, and that little blip is about 0.079 inches. And then on paper, this length is 11 inches. And so proportionally, real sedan, the measurement, proportionally that's about 25,620 inches to over 2,000 feet, about 4/10 of a mile. So if students ask, we could maybe give them that, or if you wanted to, this could be something that they do as well. Another great activity with proportional reasoning and scaling at the focus, so that maybe you want the students to figure this stuff out, and that's part of the lesson. But 4/10 of a mile. Now, that got me to thinking, as I was doing this, and I know it's a cartoon. Hey, it's a cartoon. But as I was doing this, I thought, man, 4/10 of a mile. And I was remembering Evel Knievel. Evel Knievel, as you see there in this picture, was jumping across the Snake River Canyon back in the 70s. And the distance across was 1,600 feet. And just as a reminder, 2,135 feet. So, it's in the ballpark, I guess, of something that was realistic in the Evel Knievel example anyway. And Evel Knievel failed, by the way. He did not make it. He came back down on the same side that he left because the parachute opened early and he landed on this side of the canyon. But anyway, there's Evel Knievel and his rocket trying to launch across the Snake River Canyon. And so, let's think about where rigor falls in this. Because here's one thing that I've noticed happened. We think about interesting things that students will like. And I hear teachers say this a lot. They say, oh, the students really liked that. And I'm not saying we shouldn't find things that students like to do, but the focus isn't on what did students like or not like. The focus is on what mathematics are they learning. And so this might be a really fun activity and students will like it, but let's make sure we're focused on a rigorous experience. So what questions would you ask? So you'll see this in the teacher Desmos activity, but we're going to model this. Eventually, students in their noticing and wondering come up with this idea that, well, it looks like we're going to see a parabolic path, a parabolic trajectory, and so they're thinking quadratic, and so we'll leverage that and say, sure, let's go with that, and let's work to create a quadratic function formula to model the location of Lightning McQueen as he flies across Carburetor Canyon. And before moving on, you'll see this in the Desmos, before moving on, we're going to respond to some questions first. Given that we're going to create a quadratic model, which form of the quadratic will you choose and why? Now, I think this is where the elements of rigor are going to come out, because I have to now think about the situation. I have to think about what I know about factored form, vertex form, standard form, and I'm going to make a decision. There's some critical thinking there. I'm going to make a decision about which form I'm going to focus on and why. Now, you'll see as we progress through this, it's not going to be so much about the procedural skill of writing out solving a system to get an equation in standard form, or, I don't know, doing some procedural work to get this model. We're going to use technology, we're going to use Desmos, but the critical thinking, the rigor in my mind is going to come up here where students are communicating with clarity and precision which model they're going to focus on, which form of the quadratic I should say, and why. And then another interesting thing here, there's going to be two quantities at play, a quantity x and a quantity y, and I'm going to ask the students, what do these quantities represent in this situation? So in this, you'll see quantity y here, quantity x here, as is traditional, and we have to now think about, as Lightning McQueen travels across, what do x and y represent? And this is fascinating. When I've done this with students and teachers, it's hard to get our brains away from thinking about the horizontal axis as representing time. It is not. The horizontal axis in this case is just Lightning McQueen's horizontal distance from the departure ramp. And the y-axis, the vertical axis, is Lightning McQueen's vertical axis above that horizontal as he goes across. They're both distances. There's not a time quantity in this case. That's going to come up later. And so here's what I like to do, is this, and you'll see this in the Desmos activity, is students can just play. They can choose which model, if I'm going to go factored or vertex or standard form, they can create sliders and they can just see what's going to happen. So as they slide it around, they can make a model that, there's the blip, you see the blip of Lightning McQueen there, and I just put in the little graphic there because it makes it look more fun. And you can follow the path and say, oh, in that case he makes it. But I've also seen students create models that follow the smoke trail and follow the blip because they're thinking that blip is at the vertex, and if that blip is at the vertex, then Lightning McQueen does not make it. And so there's all kinds of thinking and reasoning that goes on as we're just playing with Desmos, with thinking about what the different parameters mean, thinking about what assumptions we're making, thinking about how factored form, vertex form, or standard form work. And I love this because students always ask, are we trying to create the model so he makes it or he doesn't make it? And I just say, whatever, create the model. And you then figure out what happened. In your model, does he make it or not? And this is a great opportunity for students to think about modeling. This is where students often say things like, I love math because it's so cut and dry, it's so black and white, it's just right and wrong. But with modeling, it really isn't. We could create a legitimate model for the situation, and in one model he makes it, and in another model he doesn't. By the way, it brings up a very important question. If Lightning McQueen doesn't make it, if he smashes into the canyon on the other side, would he take advantage of his life insurance or his auto insurance at that point in time? I don't know. But anyway, modeling. George Box, famous statistician, says, all models are wrong, some are useful. So we're just trying to create a useful model at this point to talk about. So let's imagine this thing playing out. Oh, by the way, here's some of the Desmos behind the scenes, and you'll see it in that activity if you were interested. But we can create a factored form, and some students like to go with the factored form because they can see, let me back up here, I've intentionally put the origin at 0, 0. Now, that was a decision I made going into this activity, is I'm going to set this thing up for them. But that would be another way to expand this activity, is let the students make decisions about how to place the coordinate system to create the model. But I took that away from them and put 0, 0 as the where the ramp originates, and so that might make B0, make one of the intercepts 0. You only have to figure out another one, and then the parameter A. And so with sliders, you can just play around with parameter A and the parameter C and decide. Or you could go vertex form, or you could go standard form, or as students are working, and at least in my experience, there's all different forms around the room, we could have this group take their form and convert it to that form, and then they could compare work. So we could get into some procedural fluency. Take your factored form and expand it into standard form. Take your vertex form and put it into standard form. Take your standard form and put it into vertex form. So we could do that if that was a learning goal of your choice. But in this work, formative assessment, the feedback, the rigor is going to come out in how you ask the questions. We're going to let the technology do the computing and the modeling, but the rigor is going to come out not in the tedious computations, but in the questions that are asked. Which model did you choose and why? Convert from one to another. What are the advantages of the different forms? What's the advantage of putting the origin at the end of the ramp? So if I'm going to make that decision for them, I'm going to probably need to ask the students then, why was that advantageous? Under what conditions is there a successful jump? So for their model with their sliders, they might say when A is this and when B is that or whatever, they can tell us under what conditions we have a successful jump and an unsuccessful jump. And let's just suppose we wanted to focus on standard form. Learning goals, number one thing, we're thinking about our learning goals. And one of mine would be to look at a quadratic in standard form and interpret what the parameters mean. So suppose we had a standard form model. What would the negative 0.07 and what would the negative 0.679 mean? And for that matter, what do the input quantities x and y represent in this case? I asked that question earlier, but very important that we ask. So all the rigor is coming out in what we do with the model, not just in getting the model. The computer is really good at getting the model, better than humans. But what the computer is terrible at is interpreting what any of that stuff means. So I want to bring the rigor into that element of the thinking. Let's let the computer compute, and let's let the humans think and reason, communicate with precision and clarity. And specifically, I want to get into this parameter thing because maybe you haven't thought about it. What does this parameter of minus, it's a negative 0.679, what does this negative 0.07, what do they really mean? And for the sake of this presentation, we're really going to focus on this one. All right, so here's what I like to do. Imagine the quadratic term wasn't there. In case you missed it, the quadratic term just disappeared. Imagine the quadratic term wasn't there. Now what do we have? We have a linear function. And that linear function, there it is, that linear function has a slope, we might say, of minus 0.679. What would that mean? I'm pausing because I want you to be thinking about what would the slope mean in this case. Now here's what's interesting about this, I think, and interesting in a good way, awkward in a good way, is we are kind of reading this graph from right to left because Lightning McQueen is traveling across the canyon from right to left. And so what I might have to think about here is, if I think of this as 0.679 over 1, what does over mean? If I think about this as 0.679 over 1, it's for every 1 unit I travel in the horizontal direction, the vertical change is 0.679. Oh, let's do that again. For every 1 unit I travel in the horizontal direction to the left, so that would be a negative change. My vertical height changes by 0.679. That would be a positive change. Do you see the ratio? Positive to negative gives us that overall negative rate of change. But now let's put some units on it. Remember, the quantities x and y are the distance horizontally, x, and the distance vertically, y. And so we could say it like this. For every 1 foot that Lightning McQueen travels horizontally away from the ramp, his height above that horizontal is going to increase by 0.679 feet. Let me say that again. For every 1 foot horizontally, 0.679 feet vertically. The rate of change here, it's a foot per foot rate of change. And now remember the whole canceling of units thing? Well, do we cancel the units then and just say it's a unitless 0.67? No! It's different kinds of feet. It's horizontal feet and it's vertical feet. And I love that we have to slow down and think about what all of this means. For every 1 horizontal foot we travel to the left, Lightning McQueen is going to increase vertically by 0.679 feet initially. Notice right in here, that linear function and that parabola, that quadratic, are matching up. This is just the initial rate of change. That rate of change changes. And that's what this thing does. And I'm going to pause here because of my time limit, but that's another interesting examination, even at an algebra level, is to understand that the second differences of this quadratic, the changes in the rate of change are constant, and that's what this parameter describes, is how the rates of change are changing to get that quadratic model. So I love that we could ask this, according to your model, just another question we could go to with this lesson. This lesson could go on for days. According to your model, how long does it take Lightning McQueen to reach the other side of the canyon? We could bring time into this now. He has to travel a horizontal distance that we had previously, and we could ask the question, how long, and kind of come up with some parametric equations to think about x as a function of t or y as a function of t. And yeah, this thing, low floor, high ceiling. Low floor in that all students can watch the video and start thinking about this. High ceiling, you could take this thing to a calculus level and do some work with it in terms of rate of change. Now, how do we know we're right? Well, in this case, the modeling is, the modeling. We're going to have maybe around the room different models, and some will have them making it, some will have them not making it, and they can all be following that smoke trail, but it's all based on assumptions. Is that blip at the vertex or not? And we're going to have really examination by just looking at the work and articulating it, but the movie, or this little Pixar clip, does have a conclusion. Take a look.
What happened? You didn't make it. Well, see you later. Come on, guys, let's go.
Well, you didn't make it. Now this one's not quite like the baseball one where we can see our 106 miles an hour show up on the scoreboard or in the announcers talking, but it's Disney's Pixar. That's how it ended. You didn't make it. And so, just for fun. But we can, again, go back to the mathematics and have models where he makes it, models where he doesn't. Now I want to take the end of this session and talk about how do these activities play out in my classroom. And so I've recently become a big fan of Building Thinking Classrooms by Peter Liljedahl. And I'm not promoting the book. I don't get anything for this, but it's just commending to you a book that has some great resources about how to get students engaged in a thinking classroom. And specifically, I want to focus on number 3 here, the use of vertical non-permanent surfaces. And so when possible, it's not always possible because they might be working in Desmos or something, but I love the opportunity to get students standing at the whiteboards, working together, thinking, communicating, sharing in a vertical non-permanent surface space. And the reason it's called vertical non-permanent surface, because you're thinking, why not just call it a whiteboard? Well, because in Peter's research, it mattered that the work was done vertically versus horizontally. You may have those little desktop whiteboards and you're working at a horizontal surface, but Peter's research, you'll have to read to find out more about this, but Peter's research is that standing at a vertical surface has a greater impact than the horizontal. The non-permanent part, though, is good either way, horizontal or vertical, because when students are at a non-permanent surface, as opposed to, say, writing in their notebook or writing on a poster paper, the idea is they're more willing to engage and start and have that initial engagement, because if they don't like it, they just wipe it away and it's gone. And so engagement and work begins much more quickly and is more engaging when students are clustered around a vertical non-permanent surface. So I'm not going to go through all of these things. You'll have to look at this on your own. But just to give you a little glimpse, here's a picture of my classroom pre-COVID and also before we got whiteboards on all the walls. We've been working at my college to get whiteboards around the rooms. So all in this particular room now, all 4 walls have whiteboards on them. But you can see students working to solve problems. Here's another classroom. So for my classroom, about every day, for probably 75 to 100% of the day, students are here working. And I'm observing, and here's how it works. They work for several minutes. We come together and I'll have people talk and share and go back to work and come back together and go back to work and come back together. And so it's just back and forth, back and forth, back and forth, repeatedly going through different problem situations depending on the problem. Here they are working, and this is a pre-service elementary education majors working on some fraction operations. And you can see how the conversations, because of what they're thinking about, and the collaboration is just very powerful as students are doing the talking and the thinking as they work around these problems. And so all of that hopefully brings to a close this idea of rigor. That whether it's rigorously explaining how fast the baseball pitch went, whether it's rigorously getting involved in quadratics and letting computers compute, but there's other things that we can ask to get at the rigor, to get at the precision, the structure. Did you see the structure, say, in that quadratic? What do those quadratic parameters mean? Patterns, inferences, interpretation, reasoning. Developing mathematical habits of mind. That, in my brain, that pitching example gets at the habits of mind. How am I thinking about distance and time and relationships and scaling? That's a powerful way. Now I can condense all that to a formula, but can I also unpack it and make sense of it? And as they do, I believe students develop mathematics identity. This idea of, well, I'm just not a math person because I can't remember which formula to use. So helping students develop their mathematics identity. And then look, I hope you saw examples of students struggling with real, non-routine problems in context, identifying strategies to solve problems, communicating. You saw in the pictures about how students are able to communicate with clarity and precision, and they're providing justification, not justification based on I remembered a formula, but justification based on big mathematical ideas like proportional reasoning and scaling and the meaning of quadratics and quantities and covariational quantities in a graph. And so that is what a mathematically rigorous lesson, activity, assessment might look like. Now, here's some contact information for me, and also because of this virtual conference, I will be available. I'll be creating a breakout room or a virtual roundtable session. You can join me on Friday, November 19th at 11 a.m. That's Mountain Standard Time here in Arizona, and we can have some more conversation and discussion about these ideas. Please join me there if you're able. Hey, thanks so much for getting to the end of this. I hope it was useful and meaningful and practical to you and make you think maybe a little bit about the idea of rigor in our math programs, courses, assessments, lessons, activities, tasks, homework, whatever it might be. Have a great conference.